Thanks, John Thor. Coming up next, we continue our journey into HPC environments. This time, we'll take a look into the work Omnivector Solutions have done with Slurm and the canonical observability stack. For his first time presenting with us, James Beedy.
Thank you, David. Canonical provides a suite of products which improve operational capability while reducing capital and operating expenditures. That's enabled by charms and operators. An excellent way to deploy, maintain, and operate applications across public cloud and on-premise substrates. I'm here today with James Beedy, the CEO of Omnivector.
Hi, John. Thanks for having me on today.
Thanks for being with us. But before I properly introduce him, let me introduce high-performance computing. Well, you might be thinking, what is HPC? So let me give you a quick intro. High-performance computing, or supercomputing, is the procedure of combining computational resources together as a single resource. The combined resources are often referred to as a supercomputer or a compute cluster. The reason this is done is to make it possible to deliver computational intensity and the ability to process complex computational workloads and applications at high speeds and in parallel. Those workloads require computing power and performance that is often beyond the capabilities of a typical desktop computer or a workstation. So, where is it used? Let me give you a quick introduction. Commercial use of high-performance computing exceeds government and academic usage by a slight margin. The financial services sector uses clusters for portfolio management, risk and anomaly detection, and other such use cases. They do this with computational algorithms. The manufacturing sector generally splits into two parts, one being large product manufacturing, which includes the automotive and aerospace sectors. These sectors use complex computational algorithms to simulate how a vehicle might perform or be affected by the real world. And the other is the consumer product manufacturing sector. They produce your everyday items. Biosciences includes healthcare, genomics, and pharmaceutical sectors. They use clusters for anything from detection of cancer cells, simulation of organs and organisms. The energy sector uses clusters for anything from the analysis of seismic data to simulations around extraction and refinement. Then retail uses clusters for logistics, stock planning, and prediction of consumers' needs. Chemical engineering uses clusters for the creation of new materials and compounds. And the media and entertainment industry uses clusters for anything from the rendering of visual effects, or VFX, to full-blown animated movies. And then the electronic sectors. They use clusters for the creation of integrated circuits and printed circuit boards. This requires both complex designs that involve complex computation in regards to optimal placement and thermal design. Government use of HPC is second to commercial usage. It's split into four main areas: national security, national research laboratories, national agencies, and also state and local government. Academic use follows government use. They use high-performance computing for a variety of workloads. So now that you have a quick overview of high-performance computing, let me welcome James from Omnivector. Omnivector is, of course, well known in the Charming community for their excellent contributions.
Hey, John, thanks for the introduction. That was really nice of you and a little generous at that. But I'll take things from here, if you don't mind. So I'm here today to welcome everyone to a concept called software operators for HPC. As John said, my name is James Beedy. I'm the founder and CEO of a company called Omnivector. I've been an Ubuntu user for 10 plus years, and I've spent at least half that time working in high-performance compute environments. I'd like to kick things off by introducing Omnivector, Slurm, and the Omnivector Slurm Distribution. Talk a little bit about use cases, show a small demonstration running a CFD workload, and talk about how our software can be used to lower cost and reduce time to market for organizations performing simulation. So with that, let's get started. What is Omnivector? Omnivector started with the simple idea that a solution always follows a need. Taking this approach, Omnivector has built relationships with the world's largest engineering teams, developing solutions that accelerate the advancement of technology. And next you might ask, what is Slurm? No, not the squiggly yellow character from the television show. I'm talking about the simple Linux utility resource manager. The Slurm project is written in C and is maintained by SCADMD under the OpenSSL license. Functionally, Slurm is a workload manager and queuing system used in high-performance compute environments. It is capable of tracking physical resources like CPUs, memory, GPUs, servers, licenses, and other workload resources. Slurm's advanced queuing, scheduling, and plugin capabilities make it the go-to workload manager for running simulations and performing other HPC workloads. Architecturally, Slurm is comprised of 4 components: Slurm Control D, the head node or control process; Slurm DBD, the accounting and database process; Slurm D, the compute daemon; and Slurm REST-D, the API interface to Slurm. Implementing and maintaining an HPC environment is no easy task. Managing the hardware and software lifecycle becomes more laborious as HPC resources grow. Some common concerns of infrastructure managers and engineers are: how do I install the same piece of software in many different machines efficiently and securely? How do I perform operations across many machines consistently? How do I operate the software and hardware homogeneously? OSD takes aim at providing answers to these questions and brings relief for the major pain points of operating a Slurm cluster. The Omnivector Slurm Distribution is a carefully curated suite of software operators called charms. OSD is publicly available in the CharmHub software store, and to deploy and run OSD, it only takes one command, which we will demonstrate shortly. OSD enhances operability, automates lifecycle, and in turn reduces capital spend and reduces time to market in product manufacturing environments. Alleviating complexity in HPC environments ultimately leads to increasing return on investment for HPC systems. So this is where OSD really adds value in enhancing operability and lifecycle of HPC resources and decreasing time to market and decreasing capital spend for any organization. To dig in a little bit deeper, we'll take a moment to discuss what makes OSD turn. We'll start with Juju. Juju is defined as a universal operator lifecycle manager for Kubernetes operators and operators for traditional Linux applications, with declarative integration between operators for automated microservice integration. If that doesn't make much sense to you, it's okay. That's why we are here today. I will try to give some context over the next few slides. OSD uses Juju to interface with cloud APIs and to drive lifecycle events through the charmed Slurm operators. Next, the operator framework is an event-based framework designed for creating software operators. The operator framework is developed by Canonical, and the source code can be found on GitHub. The operator framework provides OSD with bindings that tie into Juju's event system, allowing the charmed Slurm operators to react and to handle the lifecycle events of each Slurm component. Operator framework enables the software operators to share information between one another. For example, OSD contains an operator for each of the primary components of Slurm. Each operator is responsible for facilitating the lifecycle of the respective Slurm component. The Slurm Control D component may need to communicate some information with the other components of Slurm, possibly to share a key or distribute a configuration. To make this happen, OSD stands on the operator lifecycle manager contained in Juju, exposed by the operator framework, to further manage the Slurm lifecycle on a component-wise basis. And so this brings us to the Slurm charms. The Slurm charms are, in fact, OSD. The Slurm charms are the curated suite of operators geared toward enhancing operability and interoperability in an HPC environment. And while we're on interoperability, it's worth noting that OSD has interoperability with other operators. Omnivector and the greater community have developed a suite of operators that integrate with OSD to provide enhanced visibility and operability of a Slurm cluster. Through Juju, OSD enables users to deploy Slurm to on-site metal, to containers on a laptop, to a public cloud, or a combination of the few. The following demo could be performed on a cloud of your choice, but for our purposes, we will run on LXD containers. So let's get on with things. We're going to now deploy a Slurm cluster on LXD containers. Following that, we'll submit a job to the Slurm SD API. And finally, we'll visualize the results of the simulation using an application called ParaView. So let's get started. Concerning the deployment of OSD, it all starts with Juju. Using Juju, we can deploy OSD to a cloud of our choosing with a single command. Running the command Juju deploy Slurm will use the built charm artifacts that live in the Charm Hub software store and will assemble a Slurm cluster right before your eyes. So let's see it. Upon entering the command at the terminal, we can watch the Slurm deployment stand up and self-assemble. Once the deployment is complete, the cluster will be ready to accept jobs. The Juju UI makes operating large deployments even easier, offering an inline terminal and sensible way of grouping and interacting with your charmed operators. The Juju UI comes baked into Juju, and it's not an additional thing. If you use Juju to deploy your workload, you also get this wonderful UI. I just wanted to make note of that, and hats off to the people who worked on the beautiful UI. Following a cluster deployment, simulation jobs can be submitted to Slurm via the Slurm REST API or a command line interface exposed by Slurm called sbatch. This example shows how we can curl the Slurm REST endpoint to submit a complex workload with ease. As part of many simulation workflows, we may want to evaluate the results produced by executing the simulation. In this example, we view the results of the motorbike workload produced by running the simulation on the Slurm cluster we just deployed. We can open the ParaView application and examine the results of our simulation, thus completing our deploy, submit, evaluate demonstration. So recapping, OSD enabled us to deploy a Slurm cluster with a single terminal command. You can reproduce this at will on any cloud supported by Juju. We then submitted a job to the deployed cluster and evaluated the results of the simulation. All of this was done in a few moments by a single person with just a few simple commands. Using OSD, simulation really is as easy as 1, 2, 3. I've listed here some of the resources used in the production of this presentation, including links to the source code of OSD, the published artifacts in the CharmHub software store, the OSD documentation, and also the scripts used to perform the simulation and demonstration on the LXD containers. And this concludes my presentation today. Thank you everyone for joining, and we welcome questions in the group chat following the presentation. Again, thank you everyone. Back to you, David.